let's look at this question here from the notes. It says, we pretty much already know how to get volumes by finding a common cross section. That's true. So we're going to rotate some dope curves. You can tell I'm on 90s kid here. Well, because I grew up in the 90s, right? People don't actually talk like that anymore. And we can find common cross section by integrating the volume of this solid revolution. So let's see if we can visualize what this looks like if I rotate it. So where am I rotating this? I'm rotating this about the x-axis. So here's what you do. When you rotate this about the x-axis, I'll put a little arrow here like that. So imagine that's like a spindle. So this line, this curve is going to come out of the board or out of the page, and it's going to rotate. And then it's going to go into the page, and it's going to go behind the page. I know it's hard to visualize. I know, but think about it. If you're rotating something, it's going to look kind of circular. So the first thing you want to do, I like to put like equal distance from the x-axis. That's a little bit higher than 2. So I'm going to go 1, 2, and put a point there because I'm rotating about the x-axis. That looks like it's kind of at 1 or a little higher than 1. So I'll go to -1. Try to make it equal distance from the x-axis, guys. Let's see, I'm trying to put the major points here, like 1.2 there, so -1.2, boom. And what other major point do I got? Way over here. So that one looks like at -2, 1, 2, 3, -2, -3, so -2, boom. Okay, so here's how it's gonna look, the moment of truth. First, reflect that one line, or the curve, right? I didn't do this one here. 1, almost 3. So 1. Okay. And then if you want to put this straight line there, that's fine. But then give it that curvature. Chavez, what do you mean? The curvature from when you're spinning it. That curve right there is coming out, and that curve is going in, like in the behind the. Do you kind of see that little? Does it kind of look 3D now? What does it look like to you? Yeah, it looks like a vase. Check it out, guys. I actually did it for you guys here. I'm actually excited to show you because now I have arrow keys. And so here's my wind plot, and here's my curve first. So all I did was I plotted this little curve first. Let me get all this out of the way if I can. I guess I'll minimize this and move this to the left. So there it is. And then I just told wind plot to rotate it. And here it is, solid revolution. And here's how it looks like. It looks like a vase. Check it out. Cool, right? And now I can actually move it up and down, unlike yesterday where I couldn't. But can you see that this is the shape that it would make? Doesn't that look cool? And okay, we're back. I can see everyone. That is good. Everyone looks happy. All right, so there it is. So now here comes the calculus part. Let me take some coffee real quick, and then I'm gonna put on my mask. Oh, I love caffeine. Huh? Oh, next time. You know what? There should be some perks for next time. Let me know. Let me know what type of white chocolate mocha for everyone. All right, here we go, guys. So now the thing is, what is the common cross section that I have? That's the key. Make sure to put the word common. It has to be a common shape over and over again, or else we can't use calculus, right? I mean, I guess we can, but there's other methods. But a common cross section. Do I cut it with respect to x? Do I cut it with respect to y? How's it going to look? Well, if you're rotating it with respect to the x-axis, if you're rotating the x-axis, it's probably going to be a dx. Sure enough, it doesn't matter where you cut it. Look, I'm going to cut it right here. Boom. That's a dx. That's a circle. Do you guys see that? If I cut it right here, it's always a circle. That slice, Travis, I don't know what you're talking about when you're saying circle. That slice there, that's a cut. If I cut it in two-dimensional, it just looks like this. Oh, it's dx because it's a vertical slice. I'm adding an infinite amount of slices. Boom, 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 boom. Dx. Yeah, we're going left to right. That's a, that is one slice. That is the diameter, that long line. You know what I mean? So how do I find area of a circle? Yeah, it's just pi r squared. Area of a circle is just pi r squared. So there it is. I got everything, guys. The radius is this line in green. That line in green is that radius of that slice. It is dictated by the curve. I got everything I need. If you wanted to do it like we did it yesterday, my cross section, A of x, is pi times, what is the radius? The radius is just the distance from the x-axis to the curve, and that curve is dictated by that. 2 plus x cosine x, close it, squared. It's the same idea. The only thing is that now we're rotating. It's the same idea. So there it is. So how do I find volume? Volume equals integral. It's pi r squared. I'm going to put the pi on the outside. That's common practice because it's a constant. I need limits. This looks like -2. Yeah. And this looks like 2. So -2 to 2. And then the radius squared. Parenthesis 2 plus x cosine x. Close the dude. Put a square on it. dx. You need a calculator for this one. You BC students will have a chance to tackle this one next year. But for you AB students, calculus AB, you cannot integrate this one with the methods that you know. BC will be able to do it eventually, but AB students at the moment, you cannot. So take your calculator out. So let me take the calculator. Make sure you are in radian mode, like always. We are. And I always freak out when I have cosine and sine and I'm squaring stuff. So I'm just going to type it into y1 to make life easy for me. 2 plus x cosine x. So there it is on y1. And then I come to the whole screen and I put pi, math 9, -2 to 2. And then I'm going to type in alpha trace y1. And then I just square it. Enter, squared, x. And there it is, guys. Voila. Did you guys get 52.4288? Did you guys get that or no? Yeah. 52.4288. I want to say, yeah, short term memory. Yep. There it is. Now, Chavez, how will it look if I don't have a calculator? Well, then they have to give you something that you know. More than likely, don't quote me on this. More than likely, if this comes out on the free response, it will be a calculator question. Did you guys realize yesterday when we did those 2 free response questions from the AP exam, they were all calculator questions? So more than likely, if they're going to ask for a volume, it's going to be a calculator question, unless it's something that you can integrate by hand. How do we feel with that, guys? Okay, let's go to the next one. Oh, I shouldn't have. I gave the answer away in there. Okay, edit for future. I put washer cross section. I was going to ask, what type of cross section is it? Edit for future. You'll see right now. Delete. And turn into question for 20, 21, 20, 22. Okay. Sorry, guys. I had to make a little note first because obviously I have to redo these notes here. All right. It says, let's do this freehand. The region in the first quadrant enclosed by the y-axis and the graph of y equals cosine x, y equals sine x is revolve about the x-axis to form a solid. Okay. Who cares about that part? Let's just do baby steps. Here comes your pre-cal. It's not extreme pre-cal. It's just baby pre-cal. I'm going to exaggerate quadrant 1. And I'm going to draw the graph of cosine x, not all of it, just part of it. Cosine x, remember that cosine starts at 1 or 0, 1. And it looks something like this. And then keeps going up and down, up and down. I'm not drawing it all because I know they're going to intersect right off the bat. And then sine x, I know that sine x starts at the origin. That's actually your point of inflection, right? Because it goes like that. And it goes like that. So the region they're talking about, let's see what region they're talking about. the region in the first quadrant enclosed by the y-axis and the graphs of cosine and sine. So they're talking about this fin-looking thing. Looks like a fin if you look at it from a certain angle. They're talking about that. It looks like a fin. So I'm going to redraw it with just the fin. So here is my second rendering, and I'm just going to draw the fin. Oh, I didn't want the wiggly there. There it is. It looks like a fin, guys. Do we know where it intersects? I hope you guys say yes. Yes. Where? See, here's where pre-cal comes in. And if you can see, guys, it's not even advanced pre-cal. It's just baby pre-cal. So if they ask you how much pre-cal do you need for calculus, just the basics. Where does cosine and sine intersect? When are they the same? At pi over something. Not everyone at the same time. Yeah, pi over 4. Cosine of pi over 4 is square root of 2 over 2, and sine of pi over 4 is square root of 2 over 2. So there it is. I know they're intersect the pi over 4. Now let's see what they want. It is revolved about the x-axis to form a solid. So remember what is being taken up there. That's the solid part. So I'm rotating. I put a little arrow, make that x-axis like a little spindle. And then you saw what the strategy that I used last time. I just try to go equal distant from the x-axis and then reflect it across the x-axis. So there it is, point, and let's see if I can do this here. And so that looks pretty good. Now let's give it that curvature, guys, that three-dimensional look. So over here, this is just blank. It's just, and there it is, perfect. Now remember, I wish you guys were here so you guys could see. I'm gonna put my hand in it. This bowl there, that's empty. That's right, like there's a table here, but that's empty, but everything else is filled, it's full. So that bowl there is empty, guys. So let's see how this cross section is going to look. So how does the cross section look, Chavez? Oh, I don't know. Let's find out. Let's find out together. You guys already know because I put the answer in there. Check it out. You're going to see it. In two-dimensional, you see that blue? That's a cross section. If I were to do two-dimensional, and I tried to, oh, wow, where'd it go? I tried to do the best I can. Remember, I got a D in art. In two-dimensional, that in blue, and you can see I'm trying to color code here, is this. You robotics people know what that is. You work with it all the time. Oh, okay. Everyone should know, I think. But maybe not. I wouldn't call it common knowledge, but I would like for you to know. That is called, in the mechanics world or a tool world, or I don't know in what world, and I guess in Earth, this is called a washer. Do we know how to find area of a washer? Of course we do, because you guys all took geometry and you guys had an awesome geometry teacher. So what is filled in? This is what's being filled in. This is anything that you see in red there is part of that solid there, right? That's what's being filled in. So how do I find area of that washer? Well, in math, this has two radiuses, right? The big radius, so the distance from here to here, they call that the big R. So they write a capital R. And then the little void here, the little circle, they call that little r. So if I want to find that area of the washer, you would say pi big R squared minus pi little r squared. And yes, you can factor out a pi, guys. Area equals pi factored out, big R squared minus little r squared. So that's exactly what I'm going to do. I'm just going to do area of a washer because that's what that cross section is. And I'll tell you something that I'm going to do that I do every year. I didn't get a chance to do it last year, but I still have the water. You guys will tell me if you guys want fresh water or not. You'll see what I'm talking about. You're like, what? What are you talking about? All right, here we go. This is a washer. It doesn't matter where you cut it, it's always going to be a washer, unless you're at the two extremes. If you're at pi over 4, you have nothing. If you're at x equals 0, you technically have a circle. But, you know, it's like a circle minus a radius of 0, so it's like your pi r squared anyways. So how do I find the area? Not the area, the volume. So here we go. I'm going to write, let me put it in red. Volume equals pi on the outside. That's what's common practice. Integral. I'm going to integrate. Give me my limits. From what to what? Perfect. Usually, sometimes. Sometimes the limits by themselves is a point, guys. 0 to power 4. Now the big R. Always use the one that will help you the most. I like to always reference a positive one because that's the one that helps me. If you want to go to the negative one, that is fine, but make sure that you know what you're doing. The big R is the distance. There it is in green. Here it is in green. The big R is this distance in green, all the way to that top curve. That's my big R. So that top curve is dictated by which one? What is that top curve? Cosine. So I'm going to write giant parenthesis, little parenthesis, cosine x, close it, put a square on it. You can say cosine squared if you want. Minus, I'm going to open a little parenthesis up. Now the little curve is dictated by this line in black. What is that curve there? What is that distance from the x-axis to that curve? That's sine x. Close it, square on it, close it, dx. Chavez, I have no idea how I would do this without a calculator. I can't integrate cosine squared minus sine squared. No, alas, yes we can. You guys took pre-cal. I think that, did I use it properly? I thought it, at least I hope so. We'll talk to Miss Grajeda, see if she agrees with how I used it. So side note, cosine 2x is equal to cosine squared x minus sine squared x. Chavez, how am I supposed to know that? How am I supposed to know that, Chavez? Well, hopefully you remember cosine a plus b is equal to cosine a cosine b minus sine a sine b. Hopefully you remember that. And if I turn that a into an x and that b into an x, that's cosine 2x, see? And cosine x times cosine x, that's cosine squared x. Sine x times sine x, that's sine squared x. All that is a side note from pre-cal. Not heavy pre-cal. So what does that mean? That means I can turn this. This on the inside is just cosine squared x minus sine squared x. So I can turn this 0 pi over 4 into cosine 2x. And that we can do without a calculator. We'll check it. We'll check that our answer matches our calculator answer. Let's see. Volume equals pi on the outside, bracket, antiderivative of cosine is sine. So I'm going to write sine 2x. If I were to do the derivative, I would have a 2 in the front. I don't have a 2 in the front, so that means I have to have a half. Close it up, 0 to pi over 4. You can include half on both of them, but I'm just gonna factor it out. Pi over 2, bracket, sine, parenthesis, 2 times pi over 4, close, close. And I can see some of you guys trying to catch up, so I'm going to slow down. See, this has its benefits, guys. If not, I would have just kept going. But minus sine of 2 times 0, close, close. So let's see, what do I have here? I have, this is sine of 0. And this right here is sine of pi over 2. And sine of pi over 2 is equal to 1, not 1, 1. Oh, that wasn't funny. I'm sorry, guys. Maybe if we had someone named Juan in here, but we don't have any Juans. So pi over 2 times 1 is just pi over 2. So the volume is pi over 2. So here's an example of a question. I don't think they would give this question to an AB student, but for you future juniors, because does that even make sense, future juniors? For you future BC students, I think they would give you this question as a multiple choice, and you would have to know your composite argument properties, your double angle. So BC would have to know a little more pre-cal than AB. But there it is, guys. Now let's check if our answer is correct. Do you guys want to check it, or we know 100% it's correct? We know 100% it's correct, right? Okay. No, but you know what? I do want to talk about cosine squared and sine squared on the calculator. All right, guys, real quick, side note. Well, not really a side note, but a quick discussion. It's very common, I see it all the time, that students, even myself sometimes, we all make mistakes, but this is a very common mistake. Like when we're trying to square cosine, because look how it comes out on the calculator. Don't worry, I'm not trying to do anything fancy here. So I'm trying to square cosine, but now look, if I do that, is that cosine squared? I don't know. I don't think it is. I think that is, I think the best route is to put a parenthesis first and then write cosine x close, and now it's squared. But see, there's too many parentheses. It's just making it look ugly. So my recommendation, anytime you have to square a cosine or a sine, I would just go to y1 and y2. So on y1, I'm going to type cosine x. On y2, I'm going to type sine x. And I'm just going to do, okay, so here we go. I'm going to go right to my home screen, and let's see if I get pi over 2. In case you want to know what pi over 2 is in decimal, let me do that first. Pi over 2 is 1.5707. So let's see if I get that answer. I'm going to put a pi on the outside. Math 9. I'm going to go from 0 to pi over 4. Pi over 4. And I'm going to go y1 squared, alpha trace, y1 squared, minus alpha trace y2 squared. And let's see if we get the same thing digit per digit. I think the calculator can handle that. And there it is, same thing, digit per digit. Cool or not cool? That's just my recommendation, guys. You don't have to do my recommendation. If you're brave, type in cosine x close squared minus sine x close squared. All right, let's continue. Whew. Are we having fun, guys? All right. If the region enclosed by the y-axis and the line y equals 2 and the curve y equals square root of x. Okay, so let me do that first before I revolve anything. So y equals square root of x looks like this. Y equals 2 looks like this. And that's going to intersect that, let's see, square root of 16. So 16, nope, 4. Square root of 4, there we go. Is revolved about the y-axis. Okay, so I'm going to rotate this by the y-axis. So that's already giving you a hint. I don't think we've done one of these yet, right? We've just done x-axis. Okay, so I'm revolving it about the y-axis. So if I revolve it about the y-axis, it's going to look like this. Let's see. Did I write enough space in there? And my common cross section has to be this. Can't. Let me draw it a little higher. There's a diameter in a two-dimensional state. That's what I have. What shape is that? A circle. But is that a dx or a dy? It's a dy. Look at the cross sections. They're all dy's. So, because it's a dy, you need to turn everything in terms of y, because that's what we're going to integrate with. So let's see. Oh, we haven't even read the question, right? The volume of the solid is given by the definition. Oh, okay, so they're doing true or false. Justify your answer. Okay, so they're saying, is this true or false? True or false? Notice they have a y in there, just like what we just talked about. Okay, let's get everything in terms of y, guys. So x equals y squared. All I did was square it. Well, it was y equals square root of x. So to get the square root out, I squared it, right? You know what I mean? We're good, right? Okay. So here we go. Area. So I'm going to put volume equals, I like to put the pi on the outside, integral. Now, these are all dy's. So the y value down here is a 0. And the y value up here, the highest point, is a 2. So far it's correct. And then my radius. The radius is dictated from the y-axis to the curve. And that curve is this one. Yes, the radius is dictated, so here it is in green, from the y-axis to this curve. And that curve is, well, x equals y squared. So that's my radius. So I'm going to write y squared, and I got to square it. There it is, pi r squared. And then put the dy. So it looks like they are wrong. Yeah, they're wrong. We're right. It should have been y to the fourth. So folks, if they would have had y to the fourth, it would have been correct. All right. You guys ready for the next one? Oh, that's your justification right there. I think that would be full credit if this were ever a free response. They would never, I don't think, this is too basic for a free response. They will ask to prove something. They will say, this is true, can you prove it? And then this will be the work that would lead to your proof. Does that make sense? All right, guys, here we go. Next one. It says, let R be the region in the first quadrant bounded by the graph. Oh, there's a fun one. I haven't seen that one in a while. 8 minus x to the 3/2, the x-axis and the y-axis. All right, so, I mean, if you have an idea how this looks, cool, but I wouldn't bother. It has decimals. You're going to need your calculator. Go to your calculator. Just type that in immediately. So I'm going to go into my calculator. I'm going to push on. I guess the batteries were running low and it turned off on me. Guys, I'm kidding. There's no batteries on my calculator. It's an emulator, guys. It's through. Okay, I'll stop. 8 minus x to the 3/2. And hopefully, oh, I put a plus in there. 3/2. Hopefully you at least know without graphing, or you would probably figure it out, I think, that it should cross the x-axis at 4 because the square root of 4 is 2 and 2 to the third power is 8 and 8 minus 8 is 0. So maybe you would be able to figure that out maybe without a calculator, but here we go. I'm going to do the standard one, zoom standard number 6. And so it kind of has like a little parabolic shape, not really because it doesn't go down on the left-hand side, it's not symmetric to the y-axis, but I just care about the quadrant 1. So now I have it in my head. I know how it looks more or less. Okay. Let's see. Let's see if we can graph this. Let's just graph the region first. I'm at the y value of 0, and then I cross at 4. And it looks something like that. There it is. Let R be the region in the first quadrant bounded by the graph that, the x-axis, and the y-axis. Okay, so they're talking about that region right there. Which of the following gives the best approximation of the volume of the solid generated when R is revolved about the x-axis? Oh, okay. So I'm going to put a little arrow here, a little arrow on the x-axis, like I'm rotating that spindle or the x-axis. And I'm going to stretch the y-axis because I'm reflecting it, right? So let's see if I can reflect first my points. And it's going to look like a dome, but on the y-axis instead of the x. And if you want to do like a circular motion here, it looks like a dome, guys, like a stadium dome. Common cross section here in blue is my one cross section. And I kind of have fun doing the little cross sections. That in blue is this shape in a two-dimensional paper. What shape is that? It's a what? It's a circle. So we're either doing circles or washers. So volume is equal to pi integral. Is that a dx or a dy? That washer. I mean, that circle, sorry. It's a dx. So my smallest x value is 0. What's my biggest one? 4. And then I just square the radius, whatever the radius is. The radius, the distance of the radius is dictated by the curve, from the x-axis to the curve. So that distance is what? Perfect. Giant parenthesis. 8 minus x to the 3/2, close it, put a square. Do not bother doing it by hand. I mean, I guess you could, but I wouldn't. So let's type that into our calculator, guys. I already have it in y1. Second quit. Math 9. Oh, let me put the pi on the outside. Second clear. Second pi, math 9, 0 to 4. Alpha trace. Sorry guys, I have to go slow here because I gotta click with my mouse. Y1 squared x, and it's thinking 361.9. There you go. All right, let's see. Do we got any more? Any more fun ones? Ooh, I see pies on this one, so I guess they want me to do this one by hand. Let R be the region enclosed by the graph y equals x squared. That's a parabola. We know how that looks. The line x equals 4 and the x-axis. It does say enclosed, so let's see what region they're talking about. So I guess first let me draw generic. X squared is this. X equals 4 is a vertical line. They must be talking about the region in quadrant 1 because that's the only region that's enclosed. Everything else is open. Do you guys see that? So they're talking about this region that I just shaded. Which of the following gives the best approximation of the volume of the solid generated when R, which is the shaded region I just did there, is revolved about the y-axis? Okay, let me exaggerate it now. So here it is. They're talking about this region. And I'm going to rotate it about the y-axis. When I rotate it about the y-axis, let's see. Maybe I should do the equidistant thing first again on this one. Oh, that was my parabola. I could have just done my parabola there. All right, there it is. Let me do a cross section. If you want to put the circular part at the very top, that's fine. It's empty. It's like an empty bowl. Not really. It's not a bowl because that's not the solid, right? But the empty part is the shape of a bowl. And that in blue is my cross section. I hope that my drawings are good enough. Do you guys see? So what I did in blue is this right here. I'm trying to color code it. I'm using colors to separate my stuff. What shape is that? It's a washer, guys. So remember that area of a washer. If you want to make a side note, I'm just not with respect to x, just with area of a washer. It's just pi big R squared minus pi little r squared. It is common to factor out a pi. So big R squared minus little r squared, where big R is this and little r is this. Let me put it in black. Now that I have all that side note stuff, I can go right into it. Oh, not yet. Is that a dx or a dy? That's a dy, guys. That slice is a dy. Infinite amount of slices. So here we go. Volume equals into pi on the outside, integral. We're not going to go 0 to 4. 0 to the highest point, way up here. What is that high point? Perfect. Put the 4 in the x value, guys, so you can figure out what that y value is. Y equals 4 squared, so y has to be 16. 0 to 16. Ooh, I like this one. Giant parenthesis. I like this one for many reasons. What is the big R? It's always that number, by the way. The big R is always what? You said it. Yeah, the big R is always 4, guys. It does not change ever. Look, go down, make another slice. The big R is always 4. Make sure to put the square on it. I do not recommend you putting 16. I recommend you writing 4 squared. So whoever the reader is knows that you found the R and you're squaring it. Minus the little r is the distance from the y-axis to that curve. And that curve is, well, I need to have it in terms of y. So let's see. X equals the square root of y. So square root of y squared. Always have the initial setup like that. Does everyone understand where I got all this stuff from? Okay, let's not use a calculator because I see all the answers in terms of pi. So that means they want us to do this by hand. So let's do it by hand. Ask. Really, it's because of the square. Anytime you have a negative, if you would have used the other one, which would I guess technically it's like negative square root of y plus minus, or the plus x equals plus minus square root of y, you squaring it and it's still going to get y. That makes sense. But on the AP exam, I think they would still give you the credit even if you put a negative in there, like inside the parentheses. Pi on the outside, bracket, antiderivative of 16 is 16y. Antiderivative of y is y squared over 2 from 0 to 16. Yeah, we can do that. 16 times 16. I want to say that's 256, right? Okay. And then 16 squared is 256 divided by 2. Well, then that must be 128. And then 256 minus 128. Well, 128 is right in the middle. So if I subtract 128 from 256, I'm back at 128. So coming back up here, that's 128 pi. I don't see any errors. I mean, I make mistakes all the time, but I don't see any errors. Are you guys having fun drawing? Yeah, it's kind of cool. We're not done yet. We got one left, but look at all these cool drawings we've done. Yeah. I'm going to go back and show my art professor who gave me a D. All these. Okay, I'll stop. I'm never going to let it go. I'm going to take that to my grave. I'm going to want that on my headstone. I got a D in art. Example 6. Let R be the region enclosed by the graph. Y equals e to the negative x, y equals e to the x, and x equals 1. Okay, you got to know a little bit of algebra. Hopefully by now we know how those two look like. Which of the following is the volume of the solid generated when R is revolved about the x-axis? Okay, first let's do what we've always done. Let's sketch a graph first, and then we'll perfect it. So let's see how y equals e to the negative x looks like. That looks like this. Y equals e to the x looks like this. And they better intersect at the same value at 1. And x equals 1 looks like this. So it's this thin with respect to the x equals 1. If the x equals 1 was an ocean, and it's like that thin right there. I don't know what else to call it. I think thin's an appropriate word for it, right? So it's that thin looking thingy in green. So now let's perfect the graph. So I'm going to make a better graph next to it. So here's my better graph. Boom, and let's see, 1, and then this one's like this, and then bam. Yeah, it looks pretty good. I think it should be closer to the x-axis, but it's pretty good, no big deal. And I'm revolving it about the x-axis, so there we go, revolve it. Let's put some points of symmetry. Point. All right, let's see. Not bad. I'm actually kind of impressed. Let's put some curvature. The empty part looks like a nuclear power plant. The little things, just the empty part, but that's not the solid. It's not, this solid does not look like that. Here comes my cross section. I'm going to change it to blue. It doesn't matter where you cut it, as long as it's a common cross section. So it looks like, boom. Make the outer one kind of thick so you can have room to put your little space in the middle. And there it is. In two-dimensional, that cross section looks like this. So we have a washer. Hopefully you had fun drawing that one little thingy here. I had a good time drawing that. That was kind of cool. I guess the next evolution is to go to a painting class and start doing solids of revolution in painting class or something. Okay, anyways, let's continue here, guys. Sorry. All right, volume. Pi on the outside, integral from lower limit is 0. Upper limit is 1 because these are all dx's. I'm going to write a giant parenthesis because I'm doing big R squared minus little r squared. The big R is the distance from the x-axis to the top of that curve. That top curve is what? E to the x, close it, put a square on it, minus, open a little parenthesis, the little r, the distance from the x-axis to that bottom one. What curve is that? E to the negative x, close it, put a square on it, close the whole thing, dx. I'm starting to look for that. The first thing I would delete is A, B, and C. They're all washers, so they need to have that pi on the outside. Next, it's between D and E, so I'm going to simplify it. Volume equals laws of exponents, 0 to 1. So there's going to be giant parenthesis, e to the 2x minus e to the negative 2x. Laws of exponents, guys. You can just multiply. An exponent raised to an exponent, you can just multiply them. So now I look for that, and we get letter D. There you go. Very cool. All right, guys, let's all come back. Well, you guys are already back. Let me come back.